fourth session, which is a lecture by the honorable speaker, Dr. Eridani from Universitas Erlangga.
Ladies and gentlemen, proceeding with the first session, and without further ado, we would like to invite the moderator, Dr. Tipan Karde. He is a retired associate professor in postgraduate college in India. Now he is engaged in visiting professor of Indian University. We would like to call Dr. Tipan Karde to come to the stage. The time is yours.
Welcome to all again. The speaker of this session is Professor Soeparna Darmawijaya, retired professor of Gajah University, and his topic is generalization of the system of real numbers. He is the retired professor of Department of Mathematics, Faculty of Mathematics and Natural Science, University of Gajah Mada. His age is now 82 years. He PhD under the supervisor of Professor Dr. Madhuma and Professor Dr. Lee. He awarded his PhD in 1988, and he was president at Indonesia Mathematical Society 1990 to 1998, and president of SEAMS in 1966 to 1967. His interested field of mathematics is theory of integrals, topology, and functionals. Now I invite Professor Soeparna Darmawijaya to present his famous paper, which is I like to enrich from his paper and lecture. Thank you, Professor Soeparna.
I am actually ashamed to speak in front of you of all, because I am too old, 80 years old, 82 years old. In this moment, I want to show that some algebra, especially algebra with commutative algebra with element,
mencoba. Ini untuk ini. Ini untuk maju mundur.
Again, we want to show that some algebra, especially commutative algebra with unit element, for example, An, the collection of all n tuple of real numbers, SR, the collection of all sequences of real numbers, and CAP, the collection of all continuous functions on interval A, closed interval AB, and MAP, the collection of all measurable functions on closed interval AB. Because algebra contains a linear space, and linear space contains a group, so we will start from group. Let G with respect to composition plus to be a commutative algebra with infinitely members. And P, we define P subject C as got the set of non-negative real numbers. Yes. If theta is a zero element member of P, if x and y members of P implies x plus y members of P. And then we write x is equal or less than y if y minus P is P. So G is a partial array of the set, and then we call G as a partial array of the group. So we call again partial of the group. If it doesn't happen, because x and y are incomparable. For example, R, the set of real number system is a commutative group. 0 denotes the null element, and P, the set of all non-negative real numbers, x and y, like as usually. R over n is greater than or equal 1, the collection of all n tuple of real numbers, and P is the set of n tuple, and y, the set n tuple in R. We denote x and y is equal to like that. This one, P is the collection of the and this one is yes. This one like that one. Again, the group is called partially ordered set, and then we define x, c, y, and x, that's y, the set of the supremum là x, phi y is the supremum, x and y and X that Y is the infimum equivalent, and R is the lattice group. Then I is the lattice group, or the second example is as R is the lattice group also. Yeah, CAP also a lattice group. So we can have a lattice group, and then we define this one. Let G is lattice group and A subset G, and A is said to be bounded as usual. It has a set in G subset where in G as a set in G subset X plus L equal set or equal set for every X in G, and Z is called usually it's called the upper bound and lower bound. P, that's X is in G and U is called supremum. If X is P equals supremum, if it is upper bound, and after upper bound is less than is greater than existent value. Also, we said A is said to be bound if A is said to be bounded if A is bounded above and bounded below. Since G is a lattice group, then we have the following theorem. Right G is a lattice group and A and B. A is said bounded above or bounded below, then the supremum and infimum of A exist. Already, if G is a lattice group and XY, XK is an increasing secant, or and bounded above, then G, then above in G, then it has a supremum. And we and the supremum or the sequence X phi minus xk is decreasing, and we write like this one. Like this one. Or we say that phi and xk is decreasing and bounded above with theta is the infimum. Also, if it's decreasing and bounded below, then we have infimum. So we write in xk and A is decreasing and have theta is infimum. It is infimum. Then we have let's give a group, lattice group, and xk and yk is a sequence in G. If the sequence is convergent to X and the sequence is and the sequence is convergent to Y, the sequence X plus Y is the secant xk and plus y is conversion to x and y, or the secant xk and yk is conversion to x minus y, and the secant xk and minus xy is converted to x minus y. This proof is follows like that, as usual. As usual to prove, I think. This is first one, usual. I think you can see the proof, like this one, and then we have the theorem, the liquid theorem. A sequence in a lattice group G is conversion if it is a Cauchy sequence. Then this is the every group is a complete. The proof is as follows. I think this is as usual the proof. I think that is the proof is a conversion to in a lattice group G. Then there is X and G such that the sequence xk and xk minus y has a infimum theta. Also in this like this one, as usual, the proof, like in the real analysis. Now, by the definition, by the last theorem, we have the following definition. G is like G appear a lattice group, X and G, and X A and subset G is called 1, X is called integral point, X in A, and for every secant xy which is converted to X, there is a positive integer and 0 such that xk number of A and the sequence xk minus x as a infimum theta. Whenever k is greater or equal to n0. X is called interior of A, denote the direction of all interior point of A. A is set called open set if every member is an interior point. The component of open set is called, if A is open set, it means if A is open set, the complement of A is a open set. It's an open set. It's a closed set. Closure set is closure of A, denote this closed set containing A. Derived set is also denote the collection of all limit points of A. This is a limit point of A if every sequence xk which is conformed to F if there is a positive integer n such that if k is greater or equal to n0, we have the sequence, this one is conformed to theta, and this one and xk intersection A is not theta, so as in real analysis also, derived set of A denotes the collection of all limit points. A boundary point denotes the collection of points also. The boundary point, I mean the boundary point is a boundary point if A, if every x, y, subset is G, which is congruent to X, that is a positive integer, and not such that for every K is greater or less, is greater or equal to. And now we have this sequence is conform to theta, and this is not non-point set. This is not a non-point set. Theta, this
Main part.
uh,
You read main part.
but the boundary of A denotes the collection of all boundary points of A. Also, an isolated point of A is not a limit point of A, but it is a limit on a HG. The proof is that the Q is lattice group, then theta, the collection of all open sets, in G is a topology in G. It's got, we count as a lattice topology, and the group is called lattice topology group. So we have group as a topology, a lattice topology group. The proof is like this one. I think as usual, point set is a number of tau, and then also also if U and V number of tau, then if U and intersection V is void, then U and intersection V is tau in a number of tau, and if there is X in U intersection V, then then every sequence X4 and G, which is congruent to X, we may choose a positive integer and 0 such that Xk number of U intersection V. And we have the sequence Xk minus A as a infimum theta. So if rho is a subset of tau, then then every X in union of this one, that is a U such that, as usual, that X is U and is an integral of U. It means that X is an intersection of union of this one. Hence, this one is an open set and a member of tau. Because the G is a lattice group, then we got a lattice topological group. And as usual, as in topology, if G is a lattice topological group and a subset G, then we have interior of R as a greatest open set contains in R also A minus theta A is an open set, and union theta G is a closed set. Closed set of the sun, and this one is also A union X. So it's a closed set, and this is a closed set. It is a closed set, and this is equal to closure of A. And we have some theorem. Fg is a topological group, is lattice topological group. And Fu is G is an open set, that X plus U is an open set for every X and G. The proof is also usual. I think the proof is usual. Now we define Fg. This is as usual. Fg and Y, Fg and H is a two lattice group. A function f from G to H is said to be additive if we have additive f. We have the following this one. Then for every f y, let G is G, and to fill that this to put the truth, and f is said to be continuous, and if is sequence if k in G, which is conform to x, implies the second and the sequence x, fx. K is conversion to fx. F is continuous in G if x is continuous at every x in G. Then we have as usual also as in a group like G and G, like G and H be lattice topological group, and F is additive, then F is continuous. It's continuous. As usual, take an operator X in G and an arbitrary sequence X which is conform to X. Then there is a positive integer and nor such that the sequence is conversion to theta. And for every whenever k less greater or equal to n0, f is in G is additive, then we have fx is additive, fx once it's done, because additive, so we have it is a 4 and is conversion to theta, and where theta is the null element of G, of H, that is f is continuous as G. So now we define let H as the topological group and G is called a lattice linear space if every A in R and X in G we have alpha X in G, which satisfies the following properties. Alpha and beta times X is called alpha X plus beta X, and alpha X plus beta times X plus Y is equal to alpha X plus alpha Y. Alpha beta X alpha beta times x is equal to alpha times beta x for every alpha beta in R and x, y, and z. F, x, and y, and z, and y, and z, we have x, we have x is equal or less than a if alpha x, if x is less or equal to y, implies alpha x is less or equal alpha y whenever alpha is a positive. Alpha x is greater than alpha y whenever alpha is negative. It is clear that the lattice linear space is generated by lattice group G, and we denote it by Vg. For every Ct, we write minus 1 times x is equal to minus x, and 0 times x is equal to theta. Null and none of G. For example, this one, a lattice group LR is a lattice linear space by defining alpha x prime is equal to this one, Example 2, a lattice group SR is a lattice linear space by defining alpha x equal to alpha, x is a symbol of the sequence, alpha times the sequence is called alpha sequence. Example 3, a lattice group SG is a lattice linear space by defining alpha f. X is called alpha fx. This one. For every x in a closed set a closed interval A B, f is in B and alpha in R. Example 4, MAB, the collection of measurable function on a closed set AB is a lattice linear space by defining this one. For almost every y, x and y, and alpha in x and R whenever f in MAB. By the collection of by the diffusion, we observe that Vg, lattice linear space generated by G is a lattice linear space is generated by G, then we denote Vg is a lattice linear space is generated by G, then we have immediately result as follows. For example, if A subject G, then A time alpha times A, x plus A subject Fg for every alpha in R and x in G. For number 2, for every x and y, members of G and P and P is real number, we have alpha x phi alpha x phi beta y and alpha x with the y axis members of Fiji. So, as this one, we have A is bounded in A, then F plus Y, F A is bounded in if A is bounded, then alpha A and X plus Y are bounded, has a supremum and infimum for every alpha in R and X in G. Now, X, the sequence is G is increasing, decreasing, and bounded above or below, then it has a supremum, infimum. Therefore, we have if X is Ft is a supremum of Xy, then Ft is a supremum of Xy, then for every X and Y and alpha in R, we have for alpha is greater or equal to 0, then we have X plus Tk and X plus Tk and alpha times Tk subset Vg, and this is conversion to this one, this is conversion to this one. F
Cover only main part. There is only 3 minutes.
Huh?
Cover only main parts of your lecture. Only main parts. You cover and skip out other.
On the other side.
Only.
Oh, no. Yes. This one? No? Now we have FFT is a lattice group, lattice linear group with tau is topology on G. Then we have tau phi, the collection alpha u and X plus u for every u member of tau, and alpha in R and X in G is a topology on a lattice linear space Fg. Then the lattice linear space G, Fg is also called a lattice topological linear Fg. Now we have a definition. A lattice linear Fg is called a linear algebra. That Fg is a lattice topological. That's one, yeah? Yeah, that's one. Yeah, again, after lattice Fg is complete, and we can also it is of lattice finite algebra. Let me see, this one is same. Again, by the definition, we have the following theorem, and then again, tau phi, the collection alpha u, X plus u in tau, alpha a real number, then and F and G. C then is the full is then TV is Tofi is the full key on lattice panel algebra. Lattice panel algebra and Fuji, and we have Fuji is lattice the full panel algebra. Now we define that P is lattice the full panel algebra. A and P in Fuji we define interval A infinity, the collection of X in Fuji alpha less than X and là sao đó. Oh. Hey. Yes, it's a fun. We define interval. We define interval. This one is the collection of X in A, alpha is less than or equal X, and this is and A, P, if A, P less or equal P, A, a closed interval like this one, as usual, is a closed interval, and then this one is A less than P, F only F we define, A and P less than P, F only F, P is a member of A in this interval, P is not equal to A, P is not equal to A, P T, for P T which is incompatible with A. Then we have A, P, this one. As usual, after we have the definition, we have the open interval like this one, and this right one, and then we have, okay. This one as an example. This one is example. The example, this one, an example of interval in R. This one in Rn, and then R minus P, then in Rn, and then this one, and this one in Rn, like this one. So number 2, in SR is a lattice panel algebra if and R is this is the sequence, and this is sequence, and we have the sequence like the sequence, and then the first and A and P, F only F, alpha J, alpha K less than K, for every K, and then we have open interval alpha infinity like this one, and open interval finite open interval like this one. N NCP, the letter Hafuna, FC, FNC, and CP. Then we have this one, first interval infinity, like this one, and then F less than G, F until Fx less than Gx for every x and G.
Excuse me, Pak Parno.
Huh?
Could we have faster? Maybe Pak Parno can present faster.
Sudah?
Faster. Lebih cepat sedikit Bapak, kalau diperbolehkan.
This one?
Ya Pak, karena waktunya sudah habis Bapak. Agak cepat lagi aja Bapak mungkin.
Oh ya.
Nggih, terima kasih.
This one is as an example NSR. Kan?
Let's come to theorem 5.5.
Ya. This one. This one. Then we have now, right? If G is let's say function alpha and a function f, a function fc, and R with formula fx and alpha, f alpha equal to alpha. Alpha E is a unit element, unit vector for every alpha in R as a property. F is a inclusion function, F is linear function, F is continuous function, and T is RF, the image of R, the image of F, the image of F is a lattice Soeparna alpha. It's a lattice Soeparna alpha, a lattice Soeparna alpha of Fiji. By the last theorem, we may consider that a lattice Soeparna alpha Fiji and here is a generalization of the system of real number, because every notion and every properties in the system of real number can be generated in a lattice Soeparna alpha.
Conclude this.
Huh?
Conclude.
Conclusion. This one is the conclusion, and this one, this one is example. Example in, for example, limit continuity and derivative of a function like this one. Example. I think in the first outer measure, number two measure per function, we have defined, we can define like usual in real numbers like this one. And huh?
You just show the. You don't need to do it.
This one?
Like it.
This is the last part. Okay.
This one? This last one?
Like it. Yeah, just.
That's one. Thank you. So, this one is the references.
Mainly you follow this pattern.
This one, I like this one. The tactile fashion, translucent, and sun. Thank you very much.
Thank you, Professor Soeparna. In this paper, valuable study matters are contained, but due to short time, this conclude is this. The summary of this, shortly, I tell you. The summary of this paper, that we like to generalize the real number from linear space, and then lattice Banach algebra is a generalized of real number system, because every property of the real line system can be generalized in the lattice Banach algebra. Here his paper in 5 articles. One is lattice group, and another is lattice topological group, and another is lattice linear space, and then lattice Banach algebra. And thank you very much for your valuable lecture, sir.
Thank you.
Conclude now. Any question from audience, and any question?
Yes?
No one. Thanks for this session, sir.
Thank you.
Thank you again, sir, for your valuable lecture.
Yeah.
We enriched from your
Okay.
lecture. Thank
Thank
you.
you, sir, very
Thank
much.
you very much.
Thank you very much to